In our class discussion, we consider everything at 1 atmospheric pressure. In this problem, we can see pressure value of 6 kilonewton per meter square. 6 kilonewton per meter square is noted. We can read this question. Air at 290 degrees centigrade flows over a flat plate at a velocity of 6 meter per second. The plate is 1 meter long and 0.5 meter wide. So we can understand this is rectangular plate. The pressure of the air is 6 kilonewton per meter square if the plate is maintained at a temperature of 70 degrees centigrade. Estimate rate of heat removed from the plate due to convection or due to the exposure of plate to air flow. Here air flow conditions are 290 degrees centigrade, fluid temperature and velocity 6 meter per second. The plate conditions are 1 meter long and 0.5 meter wide and air pressure is 6 kilonewton per meter square. Here plate temperature is 70 degrees centigrade. So we can find rate of heat loss from the plate due to heat convection. All given data are listed here. Fluid temperature T infinity is 290 degrees centigrade. Velocity U is 6 meter per second. Length L is 1 meter. Width W is 0.5 meter. Pressure of air is 6 kilonewton per meter square. Kilonewton means 6 into 10 power 3 Newton per meter square. And the plate surface temperature is 70 degrees centigrade. A plate surface temperature 70 degrees centigrade. So we need to find the heat loss Q. In our forced convection, very first step is finding film temperature TF. TF formula is TW plus T infinity by 2. Here TW means plate wall temperature. T infinity is air temperature. So TF value is 180 degrees centigrade. From our data book, properties of air at this film temperature at atmospheric pressure is rho value, kinematic viscosity nu value, Prandtl number PR, and thermal conductivity. We can note all these four values at 180 degrees centigrade at 1 atmospheric pressure from properties of air table in our data book. But in our condition, it is given pressure value as 6 into 10 power 3 Newton per meter square. 6 into 10 power 3 Newton per meter square. So here we can use this formula. Nu by nu atmospheric pressure is equal to P atmospheric pressure by pressure value given. The kinematic viscosity times pressure value at the pressure value of 6 kilonewton per meter square is equal to kinematic viscosity at 1 atmospheric pressure times pressure at 1 atmospheric pressure. We can use this formula. PV at 6 kilonewton per meter square is equal to PV or P nu at 1 atmospheric pressure. Okay, 1 bar pressure atmospheric pressure is 10 power 5 Newton per meter square. 1 bar means 10 to the power 5 Newton per meter square. So nu value is equal to nu atmospheric pressure value. It is found from data book 32.49 into 10 power minus 6 meter square per second into atmospheric pressure value 1 bar, that is equal to 10 power 5 Newton per meter square divided by given pressure value. Given pressure value is 6 kilonewton per meter square. Kilo can be written as 10 power 3. So 6 into 10 power 3 Newton per meter square. Kinematic viscosity value is 5.415 into 10 power minus 4 meter square per second. Reynolds number formula is UL by nu. Velocity times length of the plate divided by kinematic viscosity at 6 kilonewton per meter square. So we can use kinematic viscosity at pressure value given, not at 1 atmospheric pressure. So we calculated Reynolds number. It is below 5 into 10 power 5. So we can identify the flow type is laminar flow. For this case, we can use local Nusselt number formula for laminar flow against constant wall temperature condition. We know general formula. General local Nusselt number NUX is equal to HXL by K. HX means local convective heat transfer coefficient. L length of the plate. K value can be used from data book at 1 atmospheric pressure. So we can understand, we can't find a much variation if you change the pressure. But by changing pressure, we can see changes in kinematic viscosity. So they used same thermal conductivity value in local Nusselt number equation. Here everything is known except Hx. So we can find a local heat transfer coefficient Hx value. We know average heat transfer coefficient H, that is equal to 2 times local heat transfer coefficient Hx. So now H value is found. It is 2.31 watt per meter square Kelvin. Next is heat loss Q. Q formula HA TW minus T infinity. This is general formula, but here heat is removed. So fluid temperature may be high in comparison with wall temperature because heat is lost from the wall surface. So they put T infinity first. T infinity minus TW. T infinity value is 290. TW value is 70. Okay, we can convert T infinity and TW in Kelvin also, but for this difference of temperature, Kelvin or degree centigrade not affecting the difference value, so we can use T infinity in degree centigrade, TW in degree centigrade also. The Q value is 254.1 watts. I told flat plate, two surfaces may be exposed to airflow. So we can multiply Q value by 2 in order to find heat loss from both sides of the plate. In the previous problems, we found all unknowns at 1 atmospheric pressure or 1 bar. 1 bar means 10 power 5. But in this question, pressure value is not 1 atmospheric pressure, it is 6 into 10 power 3 Newton per meter square. So we can use density, kinematic viscosity, Prandtl number, conductivity at 1 atmospheric pressure and also at limb temperature of 180 degrees centigrade. Okay, we can use another equation. We can directly relate pressure times kinematic viscosity at given pressure condition to pressure and kinematic viscosity at 1 atmospheric pressure condition. So they put P given kinematic viscosity on the left side, mu atmospheric pressure and P atmospheric pressure on the right side. Here pressure given value is 6 into 10 power 3. So they kept only kinematic viscosity at given pressure condition on the left. They moved other known terms to the right by substituting mu atmospheric pressure pressure atmospheric and pressure given, we can find kinematic viscosity at a pressure of 6 into 10 power 3 Newton per meter square. Okay, next we can move to our regular procedure, Reynolds number. We can identify the flow type. Here, Reynolds number value is 1.1 into 10 power 4. It is less than 5 into 10 power 5. So we can assume flow type as laminar. We can use local Nusselt number formula for laminar flow at constant wall condition. We know general formula in terms of local convective heat transfer coefficient, that is NUX is equal to HXL by K. So we can find the HX. Average heat transfer coefficient means 2 times Hx. The heat loss Q is equal to HA times T infinity minus TW. If you see heat loss, you can put fluid temperature first, followed by wall surface temperature. Okay, heat loss from both sides is equal to 2 into Q. So total heat loss for this case is 508.2 watts. Okay. In example number, you can note the page number. It is 230. You can note the page numbers 230. I am telling you unique problems. Other problems are similar. So you can practice unique problems. Here we can see square glass plate. Area is given. Thickness is 4 mm. Heated uniformly to 98 degrees centigrade, and it is cooled by air at 20 degrees centigrade, which is flowing over both sides parallel to the plate. So both sides are exposed to airflow. Air fluid velocity is 3 meter per second. Calculate initial rate of cooling. A density value, Cp value for glass are given. Air at the mean temperature. Air at the mean temperature 55 degrees centigrade is density, Cp value, K value, nu value. Okay, we can see other values. Okay, 90 degrees centigrade, 20 degrees centigrade. So 110 degrees centigrade, 110 divided by 2 is 55 degrees centigrade. Okay, we can find density, Cp value, K value, mu value at the film temperature of 55 degrees centigrade. And the glass plate density, Cp value are also given. The glass plate area is given, thickness of the plate, glass plate is given, plate surface temperature is given, fluid temperature is given. Fluid temperature is lesser than surface temperature of 90 degrees centigrade. Fluid velocity is 3 meter per second. Okay. So we can use Reynolds number. U means fluid flow velocity. L length of the plate. Mu kinematic viscosity. In this question, we can see mu value. So we can find Reynolds number in terms of kinetic or dynamic viscosity mu. So Reynolds number is equal to rho u L by mu. Here u value is 3. Air density is 1.076. L length of the plate. Length of the plate. We can see area of the plate and thickness of the plate, but length is not given, so we can assume it as 1 meter. Okay, our Reynolds number value is less than 5 into 10 power 5. So it is laminar fluid flow. For laminar fluid flow, we can use Nusselt number equation. In terms of Reynolds number and Prandtl number, we know general NUX expression in terms of HX. So we can find the HX value. Average heat transfer coefficient means 2 times HX. Heat transfer from both sides of the plate means 2 times HA. TW minus T infinity. So H value, area, we put the length as 1 meter because only area is given. So at the length of 1 meter, we don't know cross section. So we can take it as 1 meter square. You can take it as 1 meter square. So initial rate of cooling the plate or change in temperature can be found by equating Q and mass flow rate Cp times del T. Heat loss from the plate is 952 watts. That is equal to mass flow rate can be written as A T times density. Area of the plate 1.5, thickness of the plate 4 meter, density density 2500. Okay, thickness 4 mm means 4 into 10 power minus 3. Cp value per glass plate is 0.67 into 10 power 3. Initial rate of cooling the plate. Change in temperature. The initial rate of cooling the plate means change in temperature. Change in temperature per second. Del T per second. A rate means per second. Anything per unit time or per second. Here initial rate of cooling the plate means change in temperature per unit time or per second. So delta is equal to 0.0947 degree centigrade per second. Okay, one more time I can explain. In this question, in the question itself, we can find glass plate and the air properties. We can use general Reynolds number formula, but in the question we can see Reynolds number and the kinematic viscosity of the air. So in the Reynolds number formula, instead of kinematic viscosity, you can use mu by rho. So rho can be in the numerator, mu can be in the denominator of Reynolds number formula. We can substitute all air properties applicable to Reynolds number equation. If you fix density U, L is not given. We can see only plate area and the thickness. So we can assume length as 1 meter, at which we can find the rate of heat loss and the rate of cooling the plate. The Reynolds number value is less than 5 into 10 power 5. We can assume flow type as laminar flow. For laminar flow, we can use NUX formula. Then we can use general NUX expression in terms of HX. Then average heat transfer coefficient H is equal to 2 times HX. Then we can find the Q value. Q value is HA TW minus T infinity. Here two sides of the plate are exposed to airflow. So they multiplied HA TW minus T infinity by 2. Okay, next we want del T. Change in temperature because of heat loss per unit time. So we can use this formula. Q is equal to m dot Cp del T. Okay, mass flow rate means rho times area into thickness. Rho times area into thickness. Okay, we can see Cp and del T. So you can use other values except del T by equating Q and m dot Cp del T. We can find the initial rate of cooling the plate. This is second question. Next we can see problem number in page number 257. 257. If you have book, you can turn the page to 257. Okay, page number 257. This is flow over cylinder. Next we can see one problem on flow over sphere. For flow over cylinder and sphere, okay, we can use these equations. Nusselt number equation is C times Reynolds number power m times Prandtl number power 0.333. Cm value can be fixed from data book table. General Nusselt number expression is h d by k. In place of L, we can use diameter of cylinder and sphere. So Q equation is HA times TW minus T infinity. Area equation is by dl. A cylinder surface means the periphery can be exposed to airflow. So they used by dl surface area. Okay, in A equation by dl. For sphere, Nusselt number equation is 0.37. Reynolds number power 0.6. Here area equation is 4 by r square. Q equation is same, HA TW minus T infinity. So this problem talks flow over cylinder. Air at 150 degrees centigrade, 30 km per hour flows over a cylinder of 400 mm diameter and 1500 mm height with surface temperature of 45 degrees centigrade. Calculate the heat loss. Okay, let me read it again. Air at 15 degrees centigrade, 30 km per hour flows over a cylinder of 400 mm diameter and 1500 mm height with surface temperature of 45 degrees centigrade. Okay, we can again calculate heat loss. Fluid temperature is 15. Fluid velocity 30 km per hour. Okay, we can use SI unit alone. Hour can be written as 3600 seconds. Kilometer can be written as 10 power 3 meter. So U value in terms of meter per second is 8.33. Diameter of the cylinder is 400 mm. So 400 into 10 power minus 3 meter. Length value is 1500 millimeter. So it is 1500 into 10 power minus 3 meter. Plate surface temperature TW is 45 degrees centigrade. Okay. So we rewritten all values in terms of SI unit. 1 millimeter is equal to 10 power minus 3 meter. 1 kilometer means 10 power 3 meter. 1 hour means 3600 seconds. So we written everything in terms of SI unit. Next we can find the heat loss. Okay, we can use our regular approach, that is it should start from finding film temperature of TF. TF is equal to TW plus T infinity. Wall temperature is 45. Fluid temperature is 15 degrees centigrade. So 45 plus 15, 65 to 30 degrees centigrade. So property values of air at 1 atmospheric pressure at 30 degrees centigrade is density value is 1.165. Kinematic viscosity 16 into 10 power minus 6 meter square per second. Prandtl number value 0.701. Thermal conductivity value 0.02675 watt per meter Kelvin. Okay, we noted 4 parameters. To find the other unknowns, Reynolds number value is UD by mu. Diameter is 0.4 meter. U value, fluid velocity is 8.33. Kinematic viscosity value is obtained from data book at film temperature of 30 degrees centigrade. So our value is 2.08 into 10 power 5. The Nusselt number for this case is C Reynolds number power m, Prandtl number power 0.333. Our Reynolds number value, calculated value is 2.08 into 10 power 5. In this range, we can fix C value and M value from data book table. You can check your data book. The page number is 115 in 6th edition. In the latest edition, we can see it in other page numbers. Okay, you can find this value C and M value for Reynolds number value of 2.08 into 10 power 5. So C value corresponding to Reynolds number value of 2.08 into 10 power 5 is 0.0266. M value is 0.805. After substituting everything, we can find a Nusselt number value. Nusselt number value is 451.3. We know general formula for cylinder Ht by K. Here diameter is given 0.4 meter. K value is also given from properties of air at 1 atmospheric pressure. So we can note K value, D value, Nusselt number value from previous step. Here H is unknown. After fixing everything, we can predict the H value. H value is 30.18 watt per meter square Kelvin. Then we can use general Q equation. Q is equal to HA TW minus T infinity. A becomes by dl per cylinder. So we can fix other value, H value, diameter, length, TW T infinity. Okay, after substituting value of other parameters, we can find heat loss Q value. Okay, only in cylinder, in Nusselt number formula, C and M are unknown. After finding Reynolds number, we can use Reynolds number value in fixing C and M involved in Nusselt number equation. Then we can use Nusselt number to find convective heat transfer coefficient. That value can be used in finding heat transfer or heat loss. Okay, next problem is on flow over sphere. It is not mentioned sphere, but the bulb means sphere only. Shape of the bulb is sphere. Air at 30 degrees centigrade, 0.2 meter per second flows across a 120 watts electric bulb. At 130 degrees centigrade, find heat transfer and power lost due to convection if bulb diameter is 70 mm. Air temperature T infinity is 30 degrees centigrade, fluid velocity 0.2 meter per second, and 120 watt electric bulb. So heat energy from the electric bulb is 120 watts. Surface temperature of electric bulb is 130. The TW value is 130 degrees centigrade. Diameter of the bulb or sphere is 70 mm. 70 into 10 power minus 3 meter. Here we need to find heat transfer and power lost due to convection. First step, we can find the film temperature, that is equal to TW plus T infinity by 2. We know TW value, T infinity value. So we can find TF value. Properties of air table at 80 degrees centigrade at 1 atmospheric pressure can be used to fix 4 unknown parameters. These 4 parameters are very much important in completing this problem. We can use density, kinematic viscosity, Prandtl number, thermal conductivity at 80 degrees centigrade. So we can use density, kinematic viscosity or kinematic viscosity in finding Reynolds number. Reynolds number value is UD by mu. Diameter of the bulb is 0.07 meter. Fluid velocity 0.2 meter per second. Kinematic viscosity from data book properties table of air at atmospheric pressure is 21.09 into 10 power minus 6. Here U value is given, diameter is also given. Kinematic viscosity can be found from data book for properties of air at 1 atmospheric pressure. We can fix kinematic viscosity value at the film temperature of 80 degrees centigrade. So you can find the Reynolds number value. For sphere, Nusselt number equation is 0.37 times Reynolds number power 0.6. So after substituting Reynolds number value, we can find the Nusselt number, that is equal to Hd by K. Hd by K. So we got heat transfer coefficient H of 7.94 watt per meter square Kelvin. Okay, next heat loss Q2. Earlier the bulb produces Q1. Now we can calculate Q2 value using sphere surface area H from Nusselt number equation, TW and T infinity values. After substituting everything, we can obtain Q2 value of 12.22 watts. Percentage of heat lost means heat loss due to interaction of air on electric bulb upon Q1 bulb's heat generation. The Q2 by Q1 into 100 will give us percentage of heat lost. Percentage of heat lost. This problem is flow over sphere or flow over electric bulb. In Reynolds number formula, we can change L as diameter. In data book, we can use local Nusselt number formula for sphere. General formula of Nusselt number for cylinder and sphere includes Hd by K. Next, we can equate Nusselt number value and HDK formula. In this formula, H is unknown except diameter and thermal conductivity. So we can easily obtain local heat transfer coefficient or heat transfer coefficient for sphere. For sphere topic, we can ignore local heat transfer coefficient, average heat transfer coefficient. We can tell the common name, heat transfer coefficient H. Okay, next. In this question, it is asked percentage of heat loss. The percentage of heat loss can be calculated using Newton's law of cooling. That includes surface area and temperature difference between wall and fluid. Here, sphere surface area is 4 by r square. We know radius of sphere. After substituting all known parameters on the right side of the equation, Q2, we can find Q2. Percentage of heat loss means Q2 upon Q1 into 100. In example number 3, we can see air flows over a tube. Tube can be square. Tube is circular cylinder. We can see two categories in data book. We can see Nusselt number equation in terms of C and N for cylinder. If surface is square, NC values can be fixed directly from data book value. N value is 0.675, C value is 0.092 from the data book. We know general equation. General equation in terms of C and N. C value is 0.092, N value is 0.675. We can substitute those values. So we can find the Nusselt number. Nusselt number. We already calculated Reynolds number. Okay, in the first case, we need to assume tube a square of side 6 centimeter. So length value becomes 0.06 meter or 6 centimeter. We recommend you to use SI unit everywhere. So instead of 6 centimeter, we can write 6 into 10 power minus 2 meter. Kinematic viscosity can be fixed from properties at the film temperature of 80 degrees centigrade. The next one, Nusselt number is equal to HL by K. So we can find the H value. Okay, next is tube of diameter 6 centimeter. Diameter is 6 centimeter or 6 into 10 power minus 2 meter. Reynolds number formula is UD by nu. UD by nu. So Reynolds number value 0.853 into 10 power 5. In Nusselt number equation, we can use C value, M value, and Reynolds number values. For this Reynolds number value, corresponding C and M values are given in the table. We can use everything. For cylinder case, so the obtained value is 219.3. So we can equate this value to Hd by K equation. H value is 111.3 watt per meter square Kelvin. Okay, 111.3 watt per meter square Kelvin. This is sphere. Example 2 is sphere. Example 3, it has square of side 6 centimeter, tube of circular cylinder of diameter 6 centimeter. We can see two categories. In the first step, we need to find the film temperature. We can fix the properties. We can look into case 1, in which tube side is assumed as square. The value of square of side is 6 centimeter. So we can use this value as length. So we can find a Reynolds number. For this, C and N values can be fixed by assuming tube side as square. So we can find the Nusselt number. We know general equation HL by K. So we can find the heat transfer coefficient H. The next is tube of diameter 6 centimeter. Reynolds number formula is UD by mu. Nusselt number equation C, Reynolds number power M, Prandtl number power 0.333. For this Reynolds number value, C and M values can be obtained from data book. So Nusselt number value is 219.3. We can equate this value to Hd by K, except H, other values are known. So we can fix heat transfer coefficient H if it is circular tube. If it is square tube, okay, we can get H value of 88. If it is circular tube, we can get heat transfer coefficient of 111.3. So circle increases heat transfer coefficient, so we can expect the more heat transfer if the cross section of the tube is circle. So we can know the importance of changing shape of the tube. Shape of the tube. Square tube normally known as rod. square tube, a rod, and a circular tube. A 111.3 minus 88, 30 by 111, we can expect around 40 percentage increase of heat transfer coefficient by changing cross-sectional shape from square to circular.